So we have a graph of theta versus t. Theta in revolutions, t in seconds. We do 400 revolutions in 800 seconds. That's an average of half a revolution per second. But it seems obvious that we're doing more revolutions per second at the beginning, fewer at the end. So we estimate omega bar from 300 to 400, 100 to 200, 500 to 600. Okay, so on the 300 to 400 interval, we see that theta appears to change from about 275 to 315. That'd be a delta theta of 40. Now that's just my estimate. You made your estimates. A lot of people got 50, I think. Okay? Somewhere around there. So I'm estimating delta theta revolution. This thing went around 40 times between 300 seconds and 400 seconds. So that's obvious that, you know, this is a 100-second interval, so that's your delta t. And everybody had that. So, on a graph of omega bar versus T mid, 0.4 revolutions per second might be here. Okay? Let's just say that is 0.4 revolutions per second. Then I can do the same thing from 100 to 200. So I've got another delta theta here in 100 seconds. It looks like we're going from about 130 to 210, it's about 80. So on this one, we get 0.8 revolutions per second. Well, I didn't do too bad with the shape of this graph, but 0.8 wouldn't be quite this high. Should be about here. So we'll erase that point. And at 150, we'll put that here. Incidentally, my scale isn't great. That's 150, then there's 300 here. It's not that bad. But I didn't scale this very carefully here. You'd want to scale it more carefully. And you'd still take maybe your 800 seconds and subdivide it and then put these where they belong. Okay? To get a better looking graph. And a more accurate graph. Okay, well, then between 500 and 600, well, we're on this interval. Okay? And let's just kind of indicate these are our delta t's. I think everybody understands this quite well. Okay, these are our delta t's. And here are delta theta, and obviously this delta theta is a good bit less than this one. So let's see, if that was 40, that's less than half of 40. I'm going to say that's about 15. If you've got an accurate graph, you can make more accurate measurements, and you've got an accurate graph of your theta versus t. If you don't, you need to get one. So that's about 0.15. Well, that point was a little low when I slapped it on there, but I was not trying to actually be all that accurate. But you know, down here would be 0.2. Here would be 0.1. Of course, there's 0.3, but you don't need it. And here's 0.15. So you come over here, here, and here's your point. Okay? Now, according to my estimates on this hand sketch graph, it wasn't supposed to be particularly accurate. It actually came out kind of close to what I'd expect. Straight line, it's plausible. If that straight line was a little higher, it's pretty close to all 3 points. So it's very plausible that a straight line fits this. I didn't draw it quite in the right place. But a straight line is plausible. But so is some kind of a curve through those 3 points. Another thing you know is that this curve levels off. If this thing comes to stop at 800 seconds, well, 800 is out about maybe here, so that the graph should hit the x-axis about here, which argues for the curve. Does that make sense? Okay. Well, what's the significance of a straight line versus a curve? Now again, looking at where the thing comes stationary, a straight line, if I put it just a little higher, would probably intersect about here, maybe at 700, 650. Would be that close to 800. The curve could easily go out to 800, okay? So, to decide, what you need to do is a lot more estimates. Now you actually have data. You have your omega bars, okay? I think I only saw one graph. Josh, you had it, didn't you? And the graph is somewhat ambiguous. You got a bunch of points. Across here, a bunch of points here, a bunch of points here and here. So you only get certain values for omega, since you're counting in whole revolutions, okay? And you only get up to maybe 10 or 11 revolutions of or 10 or 11 seconds for the 360 degrees, okay? When I look at this, the straight line looks pretty well, but not up here. This really argues for a curve, doesn't it? So the curve here isn't through these points, but it's kind of the kind of curve that we might well get for this day. Hey, don't trust Josh. He's a good guy, but he's human just like all the rest of us. Okay? Except me. I tend to trust him, but you know, trust and verify by doing your own work, right? And then if everybody has a very similar looking graph, we can conclude what? Okay? If this thing is a curve, then it's not a straight line. If it's not a straight line. If it's not a straight line, then the rate at which omega changes is going to differ, right? Okay, well, I think most of you had on your paper, you have the rate of change of omega bar, right? Okay, does it look like the rate of change of omega bar keeps changing? Okay, so straight line omega bar implies that omega is changing at a constant rate. Okay? That's omega bar versus T. Okay. If the curve is like this, like it appears to be from the curve that I drew and the analysis we saw, then your rate of change of omega would be doing what? Would it be increasing or decreasing? Just look at your table, and if you haven't looked at your table and thought about what it's telling you, well, it might be because that's a little hard to understand right now, right? Might be because you need to be a little more proactive with your data, okay? I mean, if you make this table and say, okay, I did it, I'm done, without thinking about it, then you don't learn as much, okay? It's important that you learn this for your future in your field and also for your grade, okay? So you want to learn everything you can, and if you're not curious about your data, try to develop some curiosity, even if you got to fake it. It can become a habit, and we had a guy here for years called drafting. He was an Air Force pilot and an engineer. And he flew with Chuck Yeager at the Eisenhower funeral. Okay? He was a significantly good pilot and a good guy. He passed away a few years ago, but you know, he kept saying that the one thing that you can't teach is curiosity, and it's the one thing that's central to any kind of high-level performance. Okay? So you're not curious about data. Like I say, I don't know how to teach it. All I'm going to say is take it and do what you would do if you were curious about it. Maybe you'll become curious. Okay? You want to know. You know, I see data, I want to, of course, I've got a lifetime of being curious about data. Okay? When I do an experiment, and we're going to do it Friday with experiments, you know, I just want to dive into it, get the data, and find out what the data's telling me. I don't do it because I have to. I do it because I just naturally want to. And of course, that's my temperament, which is why I end up doing the stuff I did. So try to cultivate curiosity. That's what I'm really saying. Okay. So, is your omega? I asked the question. I don't remember if you answered or not. I don't remember if I asked it, so let's be sure. Are your rates of change of omega, do they appear to be increasing or decreasing? Okay, on your tables. And of course, is that consistent with the graph? Okay? Well, I've got one person down there who kept saying, right. And of course, that's right. That's what that's what your data should be telling you, right? Is that what your table tells you? Okay. Is that consistent with a graph that does this? Well, let's see why it might or might not be consistent. I'll make sure the video is not getting too long, but we'll keep this thread going here, so we'll keep going. Okay. So, over here, where we're calculating the delta theta over delta t. Well, from this point to this point, I'll just bring my delta theta over here, right? And I can bring my delta t over here, like this. Okay, so now this is, make a bigger picture of it. I've got the graph, and I've got delta theta. That's a really skinny theta, so pretend you can see that, okay? Delta theta and delta t, and here's my curved graph. If I make a straight line here, then what does delta theta over delta t tell me about this straight line segment?
Rate of change.
It is the rate of change, because that's by definition, but geometrically on the graph, what aspect of the graph does it tell you? So the rate of change of omega with respect to t, the average rate of change of omega with respect to t. But on the graph, what do you call that? Well, isn't delta theta the rise? And what's delta t? It's the run. What do you get when you divide the rise by the run? You get the slope. Between these 2 points of the graph. So we're getting slopes here, right? So now we can say, well, okay, the straight line from here to here, and the straight line from here to here, and the straight line from here to here. This slope is approximately 0.8 revolutions per second. So we have these three slopes, here, here, and here. So what I've graphed over here are slopes of this graph, okay? If I want a better picture of omega versus t, well, these slopes are approximately equal to the slope of the tangent line at the midpoint, aren't they? Okay, the tangent line at the midpoint, let's take this one. So let's find a pretty color. Okay, the midpoint here goes up to here. And here is it's tangent to the midpoint at the point T omega, right? T mid, call it omega mid. Can't read that mid, but I put that subscript on there. Well, the slope of this thing is really close to the slope of this thing, isn't it? Matter of fact, if this is a quadratic function of time, the slope of the midpoint is exactly equal to the average slope between the endpoints. Very easy to prove that about quadratic functions if you know calculus. Okay? That's because the derivative of a quadratic is linear. It's related to the point that the derivative of a quadratic is a linear function. Linear function, the average occurs at the midpoint. Okay? So what I've graphed over here are slopes. Now, what's another name for the instantaneous slope of a graph? What's that represent in calculus?
Hypotenuse.
No, that's hypotenuse really isn't a calculus concept, but the hypotenuse is the length of this line segment here. Okay? Now this tangent line doesn't have a length because it's infinite length. But since you mentioned that, the length of the segment on a graph, well, that's arc length, and that can be very significant. Okay? Now some of you are in multivariable calculus or vector calculus or calculus 3, which is what we're calling it these days. That's going to be very significant, so you want to kind of store that away. Even if you haven't taken that course yet. It's in your future. The arc length is an important thing, and you see how these are close to the length. The length of each hypotenuse of the triangle is very close to the distance you'd have to move along the curve, right? As long as your interval isn't too big. Now, if you go from here all the way to here, then the curve goes significantly further than the hypotenuse would be from here to here. Okay, now back to this. If I give you function, let's say the function is t cubed plus t squared. How would you find the slope of the graph of that function at a point? You would perform a very fundamental calculus operation, which you should ideally associate with the slope of the tangent line.
Take the derivative of it.
Say no?
Take the derivative of it?
Yeah, it's a derivative. That's a question I've been asking ever since the first day. What does this make you think of in calculus? If it doesn't make you think of the derivative, it's because you don't understand the derivative. You just maybe memorize the idea that the derivative is a slope. You don't understand it. Now, you know, when I got done with calculus, I pretty much understood, but still, getting the concepts of first year calculus to reconcile with what I was learning in physics, because I was taking a more advanced physics class, because we took calculus concurrent with physics, not before physics. So I was into, you know, a more in-depth course on waves and electromagnetism and stuff. It took me the better part of my second year to reconcile what I'd learned in first year calculus with what was going on in physics, okay? But with different questions exactly like, I had as much trouble with that question as you all did, okay? Maybe not, because I think we had a little more emphasis on what things meant. But still, it's not a trivial question, so don't feel bad if you couldn't answer it, but, and don't feel bad because I say that if that question, if that answer didn't immediately occur to you, you don't know calculus. All you know is how to do some operations and stuff. You don't know what it's telling you, okay? Just another example, why do you set the derivative equal to 0 to find the maximum? Because the maximum occurs when the dang slope is 0, right? Okay? And you got to put these ideas together to some extent in physics. So anyhow, okay, so what I've just said is essentially that the slopes of this graph are the values of this graph. Isn't that what I've said? Because this is a slope that occurs at t equals 150. This is a slope that occurs at t equals 350. This is a slope that occurs at or near, say, 550. Approximated by not particularly accurate estimates, okay? Okay, so the big thing that I want you to take away from this is that omega is a derivative of theta. So now we can say that omega is d theta dt, the derivative of theta. Now, when you took physics or calculus, you almost certainly had problems like, okay, here's your position function, what's your velocity function? Okay? Velocity is one of the prime applications when you're learning about derivatives. Now, it's been, took calculus last year, it was the beginning of the year. You're probably in a distance course, and that's just difficult. But that's what it is. So you can also, this is just like this, if x is your position function. Okay? And then when you calculate your rates of change of omega, well, you're really calculating tangents to this curve, or estimating tangents to the curve, okay? Those estimates get kind of messy because of the discrete data that you have. So you want to kind of smooth everything out on the curve and then see what the slopes of the curve tell you about omega. Does that halfway make sense? And we started by measuring something that's rotating because we can get more detailed measurements of the rotation than we can of a velocity along a track or along a straight line. We can get information of those things, but it kind of comes out of a black box. Okay? So we want to get a very detailed understanding of motion and how you represent it with graphs. Okay, well, we'll go on. This video is getting long enough.